Hey guys, this video is for you to help you distinguish between the rate law and the rate expression. In a previous video, we talked about the rate expression. And let's just take a generic reaction like this. We can write the rate expression, rate is equal to minus 1 over lowercase a times the change in A's concentration over time. We could also follow the disappearance of B, its concentration over time, or we could also follow the appearance of C's concentration over time. The rate law, however, even though they're both written starting with rate, the rate law is equal to a constant that's experimentally derived times A raised to a certain power, I'll call it x, times B raised to a certain power called y. So they're both written rate equals, but this one is the rate expression. I'm going to put it in parentheses because we really don't write whether it's the expression or the law. You simply look at it and you can tell the difference. So notice first off that you can write the rate expression directly from the balanced chemical equation. The rate expression, you can look at the balanced chemical equation and just simply write it as we did in this first example. In order to write the complete rate law, however, you must do experiments. And that's shown in the fact that x and y here are both exponents that are variables. Even if we had actual numbers in place in a balanced chemical reaction, we couldn't just simply write the rate law from that. Notice that the lowercase a in front of the a does not appear as the exponent x, or the lowercase b in front of b does not appear as the exponent y. These numbers must be derived experimentally. What the difference between these two is this first expression, the rate expression, really it tells us that we can follow any particular reactant or product to determine the overall rate of the reaction. Excuse me. But in order to determine the rate law, we must conduct experiments. And the rate law will tell us something a little bit more about the balanced chemical reaction. This will tell us ultimately what exact steps are happening, called the reaction mechanism. This rate law will tell us something about the order in which molecules are colliding, and it will tell us how they are concentration dependent. This will allow us eventually, when we get to the end of this unit, to tell us what are the exact steps that take place in a chemical reaction. The overall balanced chemical reaction is not, in fact, what exactly takes place step by step, but is the summation of all those steps. But getting a little bit ahead of myself. Let's try an example here. Let's take the example of hydrogen peroxide in an aqueous state reacting with aqueous iodide ions in the presence of acid or in an acidic environment. And that gives us the products of the triiodide ion and water. In this case, if we are told that this is the chemical reaction and the rate law is K times H2O2 times I minus. If we are given this information, notice that the exponents on the hydrogen peroxide and on the iodide, the I minus, are both 1s. If nothing is written there, they are both 1s. And what this reaction tells us is that after a bunch of experiments, we're going to rewrite this equation here. After a bunch of experiments, we find that it is first order with respect to hydrogen peroxide and the I minus ion. However, if both of these are understood to be 1s, then it is said to be second order overall. So, first order with respect to the hydrogen peroxide, first order with respect to the iodide ion, and second order overall when you add them together. And that is because 1 plus 1 is equal to 2. To get the overall reaction, you add together the exponents. Let's just say for a very different reaction, we have the rate law is experimentally derived to be, let's say, NO nitric oxide, and then O2 0. What this tells us is the reaction is second order with respect to the nitric oxide, 0 order with respect to the O2, and because 2 plus 0 is 2, it is second order overall. The 0 here means that this reaction, even though O2 is a reactant, it's independent of that reactant's concentration because the exponent is a 0. So for any generic reactions, rate is equal to K times A to the 0. That A to the 0 tells us that if this reaction is, for example, A transitioning to a different substance B, it is independent of A's concentration because the rate could actually be written, because anything raised to the 0 power is 1, this rate could actually be written as K, the rate constant for that reaction. Here, if it's A going to B and it's independent of A's concentration, how could this even happen? Well, there's certain different catalysts, for example, that exist. Let's say A has to land on the catalyst, if it's a gas, in order to react. Well, that may mean that that landing on the catalyst is what, in fact, is going to be a rate determining aspect of this reaction. And so therefore, it may not depend on A's concentration at all. However, if we write K, A, and then we leave this blank, that means it's first order with respect to the A. Or we could write A squared, that means it's second order with respect to A. The only way in which we can get these numbers, whether it's 0, 1, or 2, is through experiment. That said, let's review what we just talked about. The rate law, expressed like this, is different from the rate expression. The rate law can only be determined experimentally. Our next video will, in fact, get at that point. How do you actually determine the rate law? How do you determine what the exponents are, and how do you determine what the value of K is? All right, that's it for now.